Thank you. Yep.
Okay, great. Okay. Okay, so today I'm going to talk about two projects. One is Interpreted Information Exchange, and the other one is IFC-to-OSM transformation. So OSM is for energy analysis. The focus of the first project is more on structural, and the second one is on energy analysis. But the focus of these two projects are on the design phase of projects. So this chart shows the 15 main BIM uses that is identified by PENSE in BIM Execution Planning Guide. So the focus of this project is on design phase and engineering analysis. But the concept could be used for other BIM uses. So probably you know, so I was not sure who's the audience, who's the audience, so I just put some slide for building information modeling, so I'm gonna skip those slides. And so I'm gonna start with this slide. So we, in projects, several disciplines are involved, and so we want their tool, their model to be connected. So one way is having direct translator for each pair of software we have, and the other one is having an open standard file format that can talk to a variety of different tools with different nature. So, and Building a Smart International is doing that. So I'm just briefly explaining these slides because I'm sure you know basically these standards. So we have IDN, we have IFC. So IFC is the open standard file format that is intended to be used as the common language between different tools in the AEC industry. So the first project is on Interpreted Information Exchange. So this slide shows result of a survey that is done by McGraw-Hill in 2012, I think. So on the right-hand side, you see the frequency index of different engineering analysis BIM uses, such as like a structure analysis, MEP, energy analysis. And on the left-hand side, you see the value over difficulty ratio. So if you look at that, they are either very low or even negative in some cases, such as structure analysis, MEP system, Airflow. So it means, as a designer, it's more efficient to create an analytical model from scratch instead of using your BIM model for creating your analytical model. So it means you have to spend a lot of time on creating the model and then coordinating your model with the BIM model to make sure your model is correct. So we identified two main reasons for this low value over difficulty ratio. One is low interpretability between BIM tools and engineering analysis tools. It could be a structure analysis, energy analysis, airflow analysis, any type of engineering analysis. And the other problem is the interpretation that is required after a model is imported into an analytical tool. So, for example, when you export your structural model, when you import a structural model from your BIM model, then you have to go and do the meshing, and then you have to assign loads, define like lateral loads, wind load, earthquake loads, so on and so forth. So you have to do a lot of interpretation to make the model ready for analysis. So it's time consuming. To give you a better idea of what interpretation means, consider a wall panel. That wall panel could be a SIP panel. It could be a composite light gauge steel panel, any form of composite panel as a wall. But when you want to create an analytical model, no matter what are the elements of these walls, you represent that wall with a simple shell element with an equivalent material properties. You simplify, you interpret a shell element that represent that wall. This wall could be for a structural, that is a shell element, or it could be in energy analysis, that is a surface with equivalent R value. So this is interpretation. Each time you want to export the model from BIM to an engineering analysis tool, you have to, the designer has to do this interpretation manually and then assign values to the model. Another example, this is an architectural plan of a building, but with a lot of windows, walls with different layers. But in engineering analysis, with energy model, we just simplify that with equivalent surfaces. So we interpret information for the purpose of engineering analysis. So if you look at this figure, this is showing, this is a shared BIM model. This is the engineering design analysis model. So we have some information that is specific to shared BIM model. It could be, if this is an architectural model, some architectural elements are specific to that model. They're not going to be exchanged to engineering design analysis, such as tiles, the information related to tiles in the kitchen. But there are some information that is going to be exactly the same in engineering analysis model. Between the shared model and engineering analysis model, they are the same, such as the height of a building story. So this is not information that is different. This is the same. On the other hand, we have some other information that are not the same in the architectural BIM model and engineering design analysis model. An example is the wall I just explained. So the wall has layers, has thicknesses, a lot of information in the BIM model, but in engineering analysis model, it's been transformed into a shell element. So this kind of shows the differences between different type of information exchange from a BIM model to an analytical model. So and this gives you a better understanding. On the left hand, you see a BIM model of a small structure, and on the right hand, you see a structural design analysis model of the same structure. So the column is still stays column, no difference, but like this, the slab is converted to shell elements, and that shell element is meshed alongside these joist element. And this wall has like a light gauge steel studs with some sheeting on top of that, but the whole system is transformed to simple shell element. This void, the size of the voids are not the same because this part doesn't contribute to the structural system of the model, so the size of the void is different. So that shows the difference between building information and structural design analysis model. So we identified 3 different types of information transformation between, or interpretation between a building information model and a design analysis model. One is enrichment. There are some information that are not included in BIM, but we need those things in structure, in engineering analysis tools, such as modular elasticity of the material, we might not have that in, or the strength of the material, we might not have that in BIM, but we need it in the engineering analysis model. So we have to enrich our model with some additional information. The other one is representation transformation. Here's an example. So in architectural model, in BIM model, we might represent our elements by their extruded view. So everything has a volume. While in the structural analysis, we represent elements in their topological view. So everything is a line that is connecting two points to each other. So one interpretation, one transformation is transforming the representation of elements. And the third one is simplification. It is just an example is simplification of a wall assembly to a simple shell element. So these are the three main types of information transformation. Okay, so IFC is intended to be the open standard file format that can talk with all the tools that we use in AEC. That's the intention. But IFC can represent information in many different ways. It can show the geometry, only the geometry of the model in architectural model, or it is capable of representing information in engineering analysis view. So for an structural engineer or an energy modeler, we prefer to have an engineering analytical model directly from building information models. But building information, BIM authoring tools prefer to create a geometrical model and then expect the engineering analytical tools to kind of convert those information to the format they want. So each discipline has its own preference. So the idea about my research and this interpreted information exchange is, okay, we ask the BIM authoring tools to export information in geometrical views, such as coordination view or design transfer view. And then we do interpretation of information outside of this, outside of BIM authoring tools, and then automatically create another analytical model that can be imported by analytical tools. So, but it's defining this interpretation engine, developing that, it could be very tedious. So I thought about modularizing these interpretations, and then defining one unit for each type of interpretation we do. So, but as I said before, there are some information that is going to be exactly the same in the analytical model. It's the same in BIM models and then analytical model. So we can consider a unit, a direct exchange unit, to kind of transfer those information without any changes to the output model, from input model to the output model without any changes. And then interpret other information we need and then assemble them in the output model. So we take a modular approach. So in this approach, the workflow is going to be reading an IFC file, and then it starts here, and then executing a direct exchange unit to transfer the information that's not going to be changed, and then doing the representation transformation, and then other interpretation that is required. But for this interpretation, we might need some information from external references. For example, in the wall example, so the overall strength and stiffness of the wall could be an information that we need to import from somewhere else, from the manual of the manufacturer, from a table that the structural designer has created. So this is an information that is not included in the BIM model, but we need to import it into this information exchange process. So to have a consistent way for defining these interpretation units, IU means interpretation unit. I created a methodology for defining those units. And I tried to make it, to keep it consistent with the IBM MVD development methodology that is presented by Building Smart. So in concept layer, we define what information is going to be transformed to another information. What is the input and what is the output? Just very simple definition. And then in generic layer, we define what information is required to be input to this interpretation unit, and what information is going to be the output of this interpretation. And then in the IFC layer, we define how these input and output information are represented in IFC format. So it's the same concept that we use in IDM and MVD. We define our information requirement in IDMs and then bind this information to the IFC schema to come up with MVDs. And then along this process, we might also need some external information that we define in generic layer. To give you a better idea about this definition methodology, so this is a unit. This is an interpretation unit. In the concept layer, we want to identify the live load. We want to calculate live load of building structure based on the type of space we have in the building. So we know we have codes. In code, it says if it's like a bedroom, this is the amount of live load you have to apply to your structure, to your floor system. So we want to automate this load assignment in this interpretation unit. So we want to transfer space occupancy information to live load. This is the concept layer. This is the concept layer. In generic layer, we say, okay, for space occupancy, we need to coordinate space occupancy type information in the input model, the information about the space, and information about the slab that is contained in that space. And for the live load, we have to access to the space element in the output file. We want to create a planar force and apply that to the slab surface that is interpreted in another interpretation unit. And for that, we need to have access to this IDC code, to this table, IDC code. So this is the generic layer. And then in IFC layer, we kind of show how this information is going to be modeled in IFC model, and then how this information is going to be represented in the analytical model in IFC language. So it shows where to find the information in IFC file and how to write that information, the interpreted information in the output file. So to test this methodology and this concept, I developed a tool. So if you remember, we said, let me go back to that slide. Okay, we want to do the interpretation outside of the engineering analysis tool and BIM authoring tools. So we want something outside of these. So the nature is open. It shouldn't be specific to one tool. We want it to be outside of these tools. So I created a standalone tool that has 4 modules. It's a platform. It's not a tool. It's a platform. It has 4 modules. One module is import IFC files and then parse information. One module queries information into the from the input file in the input IFC file, and then we needed a module to create new IFC instances and objects for interpreted information, and we need another module for exporting and writing the interpreted IFC file. So this is a platform, And we can use these four modules alongside with another interpretation in Gene to automate an interpretation process. So this is a platform. You can write different interpretation in Gene, one in Gene for structural analysis, one in Gene for energy analysis, any interpretation that you want, you can do that on top of this platform. But I had to do something specific, so I chose structural analysis. So okay, the whole so here we intended to develop an interpretation engine for transformation of a building information model in IFC in coordination view to a structural analysis model in IFC again, but in the structural view. In a structural model view, MVD, I'm talking about MVD. So we are converting a coordination view to structural view in IFC. So both input and output files are IFC, but represented in different MVDs. So this is a simple interpretation unit. It creates a basic structure analysis model. So for that, I define one direct exchange unit and 4 interpretation units. In the direct exchange unit, we exchange the project and unit system information, whether it's metric or it's British system. We exchange aggregation of spatial objects. I mean, whenever I'm talking about spatial objects and elements, I'm talking about buildings, projects, site, building story, which are the same in BIM authoring tools and the structure analysis. And then we have 4 interpretation units. The first one, transform linear building elements such as beam, columns, braces to their equivalent structural representation. In another interpretation unit, I transform planar elements such as wall, floor systems, ceiling to equivalent shell elements. In another interpretation unit, we add the mechanical properties of structure materials, because those things are not included in coordination view. So we need to add a module of elasticity, the yield strength, and so on and so forth to the output structural model. And then we do some connectivity adjustment, which was the most challenging unit in this interpretation in Gene. So I'm going to just to give you an example of how these units are defined and how these units work. I'm going to explain this interpretation unit. In architectural view, we represent element by the volume they occupy in space. So if I have a beam connecting to a column, so this beam is continued right to the surface of that column, not to the center, right to the surface of that column, because that's how it is in real world. It's not. It's from the surface of one column to the surface of another column. That's how we define connecting element. But look at its representation in structural view. So each element is represented by one line that is connecting 2 points to each other. And if they share one identical point, it means they're connected. So in this representation, we continue this beam right to the center of the column. And the column is represented by a center line. So this difference in representation of information causes a problem. If you don't adjust, if you import a building information model in coordination view into a structural analysis tool such as SAP or ETABS, that's what you get. Everything is broken. Nothing is connected. And the reason is what I just explained, because this element has the exact size, has the exact length that we have in real world. But it is not the same in the structure analysis view. It should continue right to the center of the connecting element, of the connected element. It's the same for wall members or planar elements. As in analytical models, we don't consider the thickness of elements. So we would have gaps with size of the thickness of elements. So this is one challenge. So if a structural engineer import an IFC model in coordination view, then he has to go and then fix all these connectivities one by one. That's time consuming. So he prefers to go and then create the model from scratch. So here, this interpretation unit is intended to automate this task and then save time. So I designed an algorithm here for adjusting coordinates of endpoints of elements to create an integrated model. So in this algorithm, we measure, these dots are showing endpoints of elements. A BIM column, shell element. So we measure the distance between these points and then compare the distance with the size, with the like a height or width of the element that this point is belonging to, that this point belongs to. So if the distance is less than the size of the element, it means they're connected. If it's less or equal. So with this method, we identify connection points and then adjust other points to be connected to that point. So in this way, we would have a connected model. Also, we do the same for elements that are connected to the middle of another point. We measure the distance of this endpoint from the other elements. It's a perpendicular distance, and then compare that with the size of elements, and based on that, we identify connection points and then modify the coordinates of this point to be equal to the coordinate of this point to be connected. So that was explanation of one interpretation unit. So in the whole in the whole interpretation process, we input IFC file, we pass project and unit system information, and then we pass the spatial aggregation information, how like the information about the height and dimension of spaces, building stories, and then we change representation first, and then we find the building elements that are contained in these spatial elements, and then from there we interpret the topological representation of those beam columns and slabs, floors from their geometrical representation in IFC file in coordination view, and then we adjust coordinates, and then we enrich the material information from external sources and write this information to the output file, and then the model is ready for being imported into the structure analysis model. So this video gives you a better sense of what this tool does. This is a simple model in Revit, beam columns, walls. So I'm going to export an IFC file in coordination view. If we import that file in SAP, this is what we get. Everything is broken, nothing is connected. Well, this is a tool I developed, so I'm going to open that file and I'm going to export a structural model, interpreting another structural model. It's created right beside the input file. So I'm going to import the interpreted file. Everything is connected. Material properties are added to the model, and then we have a model that is ready for analysis. And we further tested this tool with some of the test model that is presented by Building Smart Alliance. This is the United States airline of Building Smart International. So that was a model you could get without the tool, without automating interpretation. See, this is the floor. This is the floor level, and this is the model you get after interpreting information. And remember, that was a very simple interpretation. We can do a lot more because that was just the proof of concept. We can okay. Here the shell elements is not meshed, so we can have another interpretation unit for meshing these shells, and we can do a lot more. This is just a basic. So with that, right now we expect BIM authoring tools to implement. So we have several MVDs. We have MVDs for energy analysis. We have MVD for structure analysis, for circulation. We have a lot of MVDs. And we expect BIM authoring tools to implement all of those MVDs. But those are very expensive to implement and even more expensive to maintain for changes. So the result is we only have a couple or a few MVDs that is widely implemented by different BIM authoring tools. But having this, by implementing this interpreted information exchange concept, we only need one master MVD that could be the coordination. Coordination view is not rich enough to be the master MVD, but we just need to add a few more property sets or a few more concepts to make it capable to serve different engineering analysis skills. So we only expect BIM authoring tools to export that MVD, and then we interpret other MVDs from that master MVD. And from that, if we have one BIM tool and then one design analysis tool, we only need the BIM tool to export a model to a master MVD. I think Building a Smart Alliance is calling this the newer version of coordination view by design transfer view. So that could be a base for creating a master MVD to serve other MVDs. And then from that master MVD, we can interpret a design analysis MVD that can be imported by design analysis tools. And design analysis tools can use the design analysis MVD for coordination of information. We don't requiring a master MVD. But these design analysis tools should be able to export model in those master MVDs to be able to talk back to BIM authoring tools. So that was the first project. Eric, how much time do I have?
Another 10 minutes.
Okay, so I will go through this very quick. So this is another project. This project was funded by U.S. Department of Energy, the Consortium of Building Energy Innovation, CBI. In this project, we added the capability of importing IFC files into OpenStudio. OpenStudio is a platform developed by DOE for energy modeling, energy analysis. It's using the Energy Plus engine. So Energy Plus is also developed by DOE. So OpenStudio is using the engine of Energy Plus. So we work toward developing an add-on for OpenStudio to be able to import building information model from BIM authoring tools in IFC. So, and as I said, this is a platform. It's the platform for Energy Plus, Radiance, which is a lighting analysis tool, Design Builder, which is an energy analysis tool. So the idea was, if we connect BIM authoring tools to OpenStudio, we are connecting BIM authoring tools to a wide variety of engineering analysis, energy analysis tools. Because OpenStudio can talk with almost all of these energy analysis tools. So, but before that, let me talk about different approaches from for exporting information, exporting a model from BIM authoring tools to energy analysis tools. So one way could be exporting an analytical model, a design transfer view or coordination view, and then interpret an analytical model in the energy analysis model. When you are importing, doing the interpretation, these yellow icons are showing interpretation. So one way is relying on energy analysis tools for interpretation of engineering of an energy model from a building information model. The other approach could be doing interpretation inside BIM authoring tools. If you have a look at Revit, Revit can export a GBXML file for you. GBXML is for energy analysis. So Revit internally interpret an analytical model and then represent that in GBXML. And then you just have to import that model in your energy analysis model, because GBXML is an energy model. And the other approach could be getting information from BIM authoring tools, interpreting an energy analysis model outside of BIM authoring tools and energy analysis tools. So doing interpretation outside of these, and then exporting the model, and then importing the model into an energy analysis model. Doing that outside. So with that, you can connect a wide variety of tools. Excuse me. And this is almost the approach we took in this project. We work with BIMServer. So BIMServer was a platform in the middle that we used for model transformation. We create an add-on for OpenStudio that can talk with BIMServer. So when you import a model to OpenStudio, you send it to BIMServer for interpretation of the analytical model, and then sends it back to OpenStudio. BIMServer is a server-based BIM platform. It's online that you can. It's a server that you can get connected to and do some model transformation in there. So in this workflow, the designer creates a building information model. They export it in IFC. We import that BIM model, that IFC model, in the OpenStudio add-on we develop. We send the information to BIMServer. BIMServer transforms the IFC model to an OSM model. It's an OpenStudio model. That's the file format for OpenStudio. And then sends it back to the OpenStudio, and OpenStudio import that model, and it's a ready to analysis model. So let me skip this slide because we are short. This shows what we do internally in BIMServer. So we had a mapping between different objects in IFC schema, and then objects in the schema of OpenStudio. Like IFC wall, IFC slab, IFC roof, they have been transformed to surfaces, simple surfaces in OpenStudio model, and then lighting fixtures, they can be transformed to luminaires in OpenStudio, and it's the same for other objects. So one thing about this approach is this is based on the space. So we work with the spaces in energy analysis models. And then based on those spaces, we create bounding surfaces. So if you use that model, you would see gap between surfaces. That gap is not the real gap. This is just this is a geometric gap. These surfaces are connected, but you don't have air flowing into this gap. This video gives you a better sense of what we do in this tool. So this is a very simple two-room building information model in Revit. I'm exporting that in IFC. And this is the add-on we developed for OpenStudio. So when I click and download, it goes to BIM server, convert the model, and then send it back to OpenStudio. And now the model is imported. OpenStudio doesn't have a graphical user interface. It has an add-on for SketchUp that kind of shows the building. So this is the energy model we created from the serializer we developed in OpenStudio, and this is the gap I was talking about. So advantages of this model: IFC is meant to be the open standard export file format for BIM authoring tools. So this is what we expect from BIM authoring tools to export it, because this is their file format. GBXML, that's not the standard file format for BIM authoring tools. So since IFC can represent analytical and geometrical models, it can be used for bidirectional information exchange between BIM and energy analysis tools. But like if you use GBXML, which is a energy analysis specific tool, we cannot use it for bidirectional. MVD, one of the strong point in IFC is capability for standardizing representation of information by developing of MVDs. We don't have such things in other open standard file format that exist for engineering analysis. And then IFC is very flexible for carrying additional non-standardized objects by means of property sets. We can extend it. A user can extend it. Limitations: the transformation between representation of physical elements and analytical model were challenging, the gap that I was talking about. And another challenge is maintaining data mapping between IFC and IDD schemas, because they are changing very frequently. So we have to update these serializer and transformation tools to make sure it's working properly. Thank you. And any question? I think it was a long presentation.
Thank you very much, Issa. I mean, this is fascinating work and really sort of shows a lot of potential. I'll open the floor up to questions. I'm going to take back control of the screen. Show my screen. Okay, I'm going to get a hang of this. So if anybody has any questions, feel free to either place them in the chat window or raise your hands. I do have a couple while we wait for questions to come in. The first off is, so this is both exercises are at the sort of the prototype. Can you sort of explain at what level they are at, if they're going to be pushed out as a commercially or a freely available tool, or if they're still in development?
Well, the add-on for OpenStudio, OpenStudio is open. It's an open tool. It's available for free. You can download and use it. And our add-on is in there. If you download it, you would have our add-on. It's for free. A newer version of the interface, GUI, it will be released in a few weeks. So you already have it, but you will see a much better user interface, a newer version. and it's used as BIM server. BIM server is also open. You can have access to it. The the structural tool I developed. Well, I'm still thinking about that. I mean, I I have a basic. Can you see my screens? Can you still have it? Do you still have my screen?
I do not. Here, I'll switch it
Okay,
back.
that's fine.
It's okay. Okay.
So we would release a free version of the tool that you can use to explore IFC files, see relationships, just open a file, explore relationships, check an imported file against the schema to make sure your file is okay. So that module we would release that. It's done. It's developed. We are just working on the website to post it. Yeah, we would probably post it through the CIC lab at Penn State website. I mean, the website of CIC at Penn State.
Okay.
So if you are subscribed to that, you would receive email. I will also try to. I will send an email to your to Building Smart Canada. So you
Okay.
can also.
So we'll keep our members posted on the once that tool is delivered. What about in terms of the interpretation units you were talking? They seem to be based on the International Building Code for certain elements. How is the development of that coming along, and how many have been developed for perhaps different domains?
Well, that's what I mean. That was a concept I worked on during the past 4 years, and I think that's the only thing I develop for. The only thing we have is for structural, and so when I'm talking about like we import some information from IBC. That was just a showcase. If you have other building codes, it's just a simple built-in library in the code that we can alter to serve other codes. So those codes are very simple to alter. And for now, I've developed that only for structural, but I'm also working on developing other interpretation engine for other BIM uses. For now, I'm working on LCA for life cycle assessment and calculation of embodied energy. I'm working on that for now.
Is I guess the question of is there any relationship to the AutoCodes project that are you involved in that effort?
No, AutoCode is for checking a model against a code. Here, I don't check a model against a code, so I use a code. I import some information from a code to automate some of the modeling activities that is required to be done by designers.
Okay. Is this something that you're going to look at? Both efforts to open up in terms of perhaps escalating it to Building Smart International level and having perhaps a room developed around it. And I mean, the other question is, how would one get involved in this particular effort should it be opened up?
Absolutely. Well, as I said, I have developed a platform that could be. This is in C++. I have different modules, so absolutely, I would be very interested to collaborate with researchers that can or software developers that can use that platform and then build on top of that. Absolutely.
Okay. So should we just so we can contact you directly if there's any interest?
Absolutely.
Okay. So we'll be providing your contact information in our newsletter just as a follow up.
Cool.
I'm going to look at I have a question here. So there's a question about what's the difference between existing options in most structural software like merge nodes, joint points, or structure corrections in Tekla or Robot. What's the difference between what you've developed and these existing options in existing tools?
Well, for each of these, this is developed. This is different for robot. So when you create a model in Revit, Revit creates another structure analysis model in parallel with the BIM model. So when you are drawing a model, so it monitors your clicks, and then based on your clicks, identify joints, and then create an analytical model in parallel with your BIM model. So when you export from Revit to robot, it's that model that is going to be exchanged. Revit is not interpreted in other models. So it has already created a model when you were drawing the model. So if you want to test that, import the model into Revit from somewhere else. Draw a model from ArchiCAD, import it into Revit. Since you have in IFC or any other language, then you cannot export a structural model to robot because you didn't create that model in Revit. So the structural analysis model that was in parallel with BIM doesn't exist anymore.
So it's.
But
go ahead.
And for the other one, for merging, when you go to other software, first of all, merging point was one interpretation unit in this workflow. This is one of the things, one of the issues that structural engineer faces. And the other one is when you merge with these merge points in those tools, you specify a distance. Okay, you say merge all the points that are closer than 25 centimeters. So, but here the merging is based on the size of elements that are connected to that point.
Okay, excellent. The other one is, does your tool deal with eccentricity and gaps between beams and columns?
Yes.
Okay.
Beams, columns, and floors, everything.
Excellent. So I guess we're on time, and I'd like to thank you for your excellent presentation. As I said, we'll follow up with in our next newsletter with your contact information if anybody wants to get in contact and further the discussion. Our next monthly meeting will be December 21st at 12 p.m. It'll be our last meeting this year, and we'll have Daniel Barbeau from CANAM that will be presenting the ICE district. Donc, notre prochaine rencontre des membres sera le 21 décembre, encore à midi, et ça sera Daniel Barbeau de CANAM qui présentera l'aréna à Edmonton. I'd like to thank everybody for being here and see you next month. Thank you very much, Issa.
Thank you for inviting me. It was a pleasure.